All right, welcome to it. We are streaming yet again. And this time, we're going to be talking about exponential functions and exponential equations and expressions and all that good stuff. All right, so let's go ahead and start. Let's just do this. I'm going to grab this guy right here so that we can go ahead and just start talking about what it means to be an exponential function. All right. All right, so exponential functions. Our basic exponential function is going to look like this. Actually, I'm going to do this in red. Just because there's one particular kind of guy that I like to work with. But this is just the generic form. So f of x is equal to a to the x. So what's going on here is that we have something that's just a little bit different. Because now we're working with x being the power as opposed to the base. Like we've seen before when you have x squared, how to work with that. Where you just keep plugging in numbers and you keep squaring it. Okay. But here it's a little bit different. Now you're going to have a fixed base and you're just going to keep raising it to a different power. Now there are some conditions about this. So the value for a has to be greater than 0 and the base cannot equal 1. Because if you have a base of 1, that means that no matter what power you raise that to, you're always going to get 1. And that's going to just negate the whole idea of an exponential function. So with these exponential functions, we're talking about things that when you look at the graphs, they're going to kind of start out kind of slow and they just kind of ramp up over time, ramping up a lot faster than what you're going to see with say a squaring function or any other kind of polynomial function. I know we've seen those guys get pretty steep on the end, but the exponential functions is just going to blow it out of the water. Now, having the base be greater than 0 does allow us to have things that are less than 1, but we're not going to deal with negatives for the base. Now, the power can be negative, but we just don't want to have that for the base. And the reason for that is because the power is not going to be limited to just integer values, right? So we might have things that are, say, to the 1/2 power. So, x could be 1/2, which means we're talking about a square root. And you don't want to be throwing a square root onto a base that's negative because now you have imaginary numbers and it just gets really, really messy. And you start to, lose the continuity of the exponential function. For the key values for an exponential function, you're going to see this. If you plug in -1, you get the reciprocal of the base. If you plug in 0, you get 1. If you plug in 1, you get just the base. All right. Now, in the past, we have talked about a lot of parent functions where you have the origin being some kind of like anchor point there. And we would plot that vertex or that key point and then we kind of build from it. So if we're talking about the parabola, the squaring function, we just build from there. If we're talking about the square root function, you start there and you kind of curve up and out to the right. Here, and also kind of what we saw with the rational functions, we don't have the origin as a point on the parent function, but we do have this guy right here. We've got this ordered pair 0, 1. So no matter what exponential function we're working with, 0, 1 is going to be our I would call it a base point. I like to call it an anchor point because it's going to be there no matter what the base is. You see, it doesn't depend on what a is. Because whenever you raise a number to the 0 power, you get 1. The only exception to that is if you do 0 to the 0 power. But you know what? We're not going to be doing 0 to the 0 power because we already have that restriction on a saying that a has to be greater than 0. So you're never going to run into that problem. Now, the example that I like to do a lot of times with my students is to have f of x equal to 2 to the x power. So we can have really whatever base we want to. I could do a base of 3 or 10, but in terms of getting nice points that we can see and work with, doing a base of 2 is great to help us understand just how an exponential function is going to work. All right, so let's do a table of values and see what happens here. If I go off of what I see there in red, just to the left there, it seems to me that if I plug in -1, I should get the reciprocal of the base, so I'd get 1/2. If I plug in 0, I'm going to get 1, always and forever. And if I plug in 1, I'm going to get 2. Now, I hope that makes sense to us as we're looking at this. So let me look at it over here to the side. If I take 2 to the negative first power, that means 1 over 2. We've seen that with negative powers before. So let me just remind you of this, that when you have a to a negative power, you would do 1 over a raised to that power, right? So the negative doesn't give you a negative number, it just causes you to do the reciprocal. Now, if I were to keep going on with some other values, go plug in 2, then you're dealing with 2 squared, but that's just going to be 4. If I do 3, I have 2 to the 3, and that's going to be 8. So what I want to do here is I want to plot these points so you get a good sense of what's going on with this function. All right, go to our trusty purple color. We have -1 is going to give us 1/2. 0 gives us 1. 1 gives us 2. 2 is 4. If I plug in 3, I'm going to end up here at 8. Now, what's happening here is that we have this exponential growth as we go from left to right. When the base is 2, or really whatever the base is, each step that I go to the right, I'm going to multiply my base. I'm going to multiply the previous value by that number. So you see here we started off with a value of 1. And that's a value of 2. This height is 4. This guy is 8, and so on. Each successive step I take is going to multiply times my base here of 2. So if I go out to when x is 4, add 2 to the 4th, so it's going to be 16. And then I multiply that times 2, I get 32. And then 64 and 128. So as I go across here, this guy's just going to start blowing up as I go out to the right. Even if I try to go over here to 10, right? That means I plug in 10, I'd have to work out 2 to the 10th, which, cool enough, is 1024. 1024. Like MathMan 1024. Who knew? But if you think about how this would compare to, say, the squaring function, if you had x squared and you plugged in 10, 10 squared is 100. It seemed big at the time, but it pales in comparison to 2 to the 10th, which is 1024. All right. Now, like I said, as I go up to the right, each step I'm going to be multiplying times that base. Reverse that as you go to the left, and you'd be dividing by that base. So half of 8 is 4, half of 4 is 2, half of 2 is 1, and then you get 1/2. If you keep going down to the left, you'd have half of a half, which is a 4th. Half of a 4th, which is an 1/8, and then a 16th, and then a 32nd. It's the same kind of divisions that you would see on a ruler or any kind of tape measure, right? Of course, you got the halves there, but then they take the halves and they do half of that to get the quarters and the eighths and so on. All right, so let's connect these dots so we can get a sense of what's going on here. So as I go to the right, this guy is just blowing up. And as I go to the left, he is getting smaller and smaller and smaller. And he's going to quickly be approaching 0. But here's the thing. It never actually gets to equal 0. It just gets to be close to 0. Because what's going on is that we have something from when we were talking about rational functions, we're going to have an asymptote. So we have this horizontal asymptote of y equals 0. Right? Now, when we talked about asymptotes, we've talked about how the vertical asymptotes are those lines that you just can never cross. You can cross a horizontal asymptote, but for these exponential guys, you're not really going to see that. And also when I talked about horizontal asymptotes before, I said that it refers to the end behavior. Now, for our rational functions, it really meant the end behavior for whether we're going out to positive or negative infinity. For exponential functions, it's a little bit different. It only describes the end behavior on one end. Because if you look at this graph, on one end, he's getting really, really, really small as he's approaching 0. He's getting closer and closer to the horizontal asymptote. On the other side, he's blowing up. And so there's nothing to describe the end behavior on the right side of this graph because he just blows up. Now, some students will look at this and think, oh, he's getting really, really tall. Does that mean he's coming up against a vertical asymptote? Nope. And the reason for that is because when we look at our domain and range, and let's just keep this with the 2 to the x function that we see here, the domain is going to be all real numbers. And if the domain is all real numbers, there's never going to be a place where your function is undefined, and that means there's no place where you could ever have a vertical asymptote. My range is as you go from bottom to top, so we're going from 0 and we're going up to infinity. Now notice I've got parentheses on the 0. You've got that horizontal asymptote, so as I go to the left, I'm getting closer and closer and closer to it, but I don't ever get to equal that. Because think about it, we keep making those divisions. We go, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128th. They're getting smaller, and you could get to the point where, for all practical purposes, you would see that as 0. But in reality, in terms of the way numbers work, it's never going to equal 0. So that's why we got parentheses on the 0. All right. Now, all the graphing techniques that we've talked about so far, where you can shift things up, down, left, and right, or reflect across the x-axis, all that's still going to apply here to our exponential function. None of that changes. The techniques work exactly the same. What you need to be able to do is to replot your horizontal asymptote where it's supposed to be, and then find this anchor point, right? Find that as your reference point, and then build from there. So we're going to look at some examples of that here in just a moment. But I want you to see another example here. Let's change the base a little bit. So if I say f of x is equal to 1/2 to the x power, right? So just like all the stuff that we've seen, we can come up with a t-table of values. Now, what we saw before is that if I plug in -1, I'm supposed to get the reciprocal of the base. So if the base is 1/2, the reciprocal is 2. And then there is the old standby. If I plug in 0, I should get 1, because anything to the 0 power is 1, except 0 to the 0. If I plug in a power of 1, I should just get that base that we see, which is 1/2. Now, in the previous example, my base was 2. So every step I took, I was multiplying times that base, which is why I went 1, 2, 4, 8, 16, and so on. Here, now we are going to start right there at 0, 1. Every step I take to the right means I'm multiplying times my base, which is 1/2. But if I do 1 times 1/2, I get 1/2. I do 1/2 times 1/2, I get 1/4, and so on and so on. So I'm getting smaller as I go to the right because my base is between 0 and 1. So this would describe something that is what we call exponential decay, where you are left with half of your previous amount each time. It's not half of the original, it's half of the previous amount. Okay. Now, just like we had before, if I were to go backwards, if I go to the left, I would be dividing by 1/2. That's one of those weird things that when you think about it, it seems like, oh, I'm just doing half. No. If I say we divide by 1/2, that's the same thing as saying multiply times 2. Right? So as I go to the left, multiply times 2. So 1 times 2 is 2, times 2 is 4, times 2 is 8. Now, we're going to see a graph that looks very, very similar to what we had for 2 to the x. Except now, instead of blowing up as I go up to the right, this guy is going to meet his maker with this horizontal asymptote that's still in place there at y equals 0. So that's what 1/2 to the x would look like. Now, let's just kind of go back and forth between these. So you got this guy that is decreasing because the power is 1/2. And up here, this guy is increasing because he has a power of 2. All right. Hopefully that seems to make sense. Like for this one exponential, this 2 to the x, you can think about that as like every day you're doubling something. So you start with 1, the next day it's 2, then you double that, the next day it's 4, you double that, the next day it's 8, and so on. Whereas when the base is 1/2, each day that you go on, you have half of what you had the previous day, and then half of that half, and so on and so on. So the little name that I like to give these graphs is I call them the Genie function. So if you remember Disney's Aladdin from the early 90s, the animated, we're not talking about the live action stuff, we're talking about when animation was good, right? When the story was good. And if you remember, there's that scene whenever Aladdin meets the genie, and he's like, oh, it must be great to be a genie. And you see that there's that one part here where you have this phenomenal cosmic power, right? But what's the downside? Itty bitty living space, right? So think about this as your Genie function. On one end, he blows up. On the other end, he gets really, really, really tiny as he approaches that horizontal asymptote. All right, so now let's look at how we would graph with our translations. So let's do 2 raised to the x, let's say -3, and then let's do -4, like that. What we need to recognize here is that we have x in a power, so that makes it an exponential function, and we need to know, identify the basis too, so we have an idea about the graph. We know there should be this horizontal asymptote, and because my base is something that's larger than 1, I expect it to be really small before it blows up as it goes out to the right. All right. The rest of this is making sure that we can clearly understand where these numbers are, right? So part of that is going to be how will you write things so that it's neat and easy to read. We have the inside part of the function, which might be kind of hard to figure out. It's not like having parentheses with a square or having things inside of a square root or inside absolute values. Here, that's the inside part of the function. And because I see the -3 there, this -3 tells me that I'm going opposite of what I see. So it means I would go to the right 3 units. And the -4, which is completely outside of the power function, we do exactly what we see here, which means we're going to shift down 4 units. All right, and that's going to be one of the first key guys that we look at doing. So our normal graph has this horizontal asymptote at y equals 0. We're going to grab this guy and move him down 4 units. So we have a new horizontal asymptote of y equals -4. So let's go ahead and graph that, making sure that we know what's going on here. All right, so I keep that there. I know it's a dashed line. It's not really part of the graph. It's more like guidelines for us, okay? But now let's look at this other part. We'll go to the right 3. So if I go to the right 3, I would be kind of right here. Now, I'm not making a full-on dashed line from top to bottom because I fear that if you do that, you might get confused and think, oh, this is another asymptote, but it's not. So I'm just drawing a small little part right here, and I'm going to do like a quick little circle there, not a full point, but just a circle to remind myself that this is I'm going to treat this as my new origin. Now, the value that you're going to, the order pair that you're going to have for all these guys is order pair 0, 1. So I'm going to start right there, 0, 1. Since my base is 2, every step I take to the right, I'm going to multiply that times 2. So I don't need to worry about going right 3 or going down 4. I've already done that. So as I go to the right, I multiply this times 2. Now this has a distance of 1 right now. This is going to give me a distance of 2. Go another step. The distance should be 4 units between the point and the horizontal asymptote. Do it again. The distance here will be 8. All right, just like we saw before. If I did another step, then my distance would be 16, which is going to take me off the chart, and where's the fun in that? All right, so we're just going to connect the dots as we go to the right. Now, here's the thing. I said if we go one more step, it would take me off of the grid. So I should be aiming to where that next part is going to be, and I really shouldn't be crossing over that next part because I know the order pair is going to be somewhere up here at the top. So I'm just going to aim in that direction. On the left side of this graph, you're getting smaller and smaller because you go from 8 to 4 to 2 to 1 to 1/2 to 1/4 and so on. So I end up doing this a lot. I have to rotate my picture, rotate my graph, so I can get a very nice graph going on over here. Now remember that this guy is going to be getting closer and closer to that asymptote there on the right. So don't come back and then curve up. It doesn't work that way. So that's how you graph it. So it's the same graphing techniques that we've already seen. There shouldn't be anything new here. Now, let me show you this though. If I change this up and I do, let's do an orange. I think that'd show up. If I did g of x is equal to 3 raised to the x minus 3 minus 4, he would have the same starting point right here at the 0, 1. But since my base is 3, every step I take along the way, he's going to be multiplying times 3, which means his next step is going to be 3. The one after that is going to be up here at 9. And then the one after that's going to be 27. So he's already way off the grid, right? So having a larger base means that you're going to be blowing up a lot faster. You're going to be a lot steeper there. And on the back side of this, it means you're going to be getting a lot smaller when you are on the right side of that key anchor point. So it means you'd be down here 1/3 and then 1/9 and so on. So the higher the base is, the steeper the graph is going to be as you start to blow up on the right, but then the flatter you're going to be as you come over here to the left. So you saw that I could only really get just I think 3 nice points there, and to me, I don't want to do that. I like to have a base of 2 because you get to have, you get this point, that one, that you get 4 really nice points, and a 5th one if you want to look at the one that's the half mark. Right. So I like doing that, and I definitely don't want to do what you see in some textbooks or some other homework you may have come across with, oh, let's have the base be 10. Think about what happens if the base is 10. You go from 1 to 10 to 100. So you can't even get 2 points out there because you've already blown up and you're off the grid. So in terms of graphing and understanding how does this work, I like to use a base of 2 or maybe a base of 1/2. Now, let me do another little alteration here so we can see the differences. Whoops, that is not what I did. I mean, it is what I did. I didn't mean to. So if I do h of x is equal to -2 raised to the x minus 3 minus 4. Well, how different should this be? What's changed? The only thing that's changed is having a negative in front of your base, in front of the main part of the function, which is a reflection across the x-axis. So we've turned it upside down, but we still have the same shifts and translations here where we're going down 4 and to the right 3. So now this is still going to be the new origin, so to speak, but you're going to be upside down, starting right there. Go one step over, you go times 2, another step, times 2 is going to give you 4, and then 8, and so on. So you have, basically that purple graph, and he is reflected to be upside down. So this is what it would look like. So The graphing techniques are still sound. They're still the same thing that we've always done. It's just learning a new shape. And that's really it. Nothing more than that. Now, let's have some fun. All right, so one of my favorite things to do is to play around with exponential equations. All right, so exponential equations. As crazy as it sounds, exponential equations are equations where your variable is in the power. All right. The simple way to work this is to remember this one statement. If you have a to the x is equal to a to the y, then the conclusion is that x is equal to y. Right? So, in other words, if we can write things so that we have the same base on both sides, the only way this can happen to have an equation is if the powers are exactly the same. So you're going to see something like this. If I say solve 7 to the x equals 49. Now, I hope that we could all look at that and just know what the answer is. But it's important that we understand that both sides of the equation could be written as a power of 7, because 49 is 7 squared. And since these guys have the exact same base, the only way that this equation can be true is if the powers themselves are the same. And so you end up with an equation. This one's already has x by itself, so x equals 2. So for right now, for a lot of these problems, we're just trying to identify a base that's common for both sides. For example, if I say 8 to the x equals 4. Now, these guys are, they don't have the same base, but can I rewrite it so they do have the same base? Now, in order to do this well, you're going to need to know your powers. So, sometimes students look at 8 and they go, oh, 8 is 2 times 4. I don't really care about that. What I care about is being able to write each side with the same base. So that means you need to know your powers. And here's the thing. If I try to say, oh, these are powers of 4. All right, so 4 to the first is 4. But 4 squared is 16. So the common base here is not 4, because you can't raise 4 to a nice power to get 8. However, let's think about what 4 is made up of. 4 is composed of the factors 2 times 2. So we know that 2 squared is equal to 4. Go to the next power of 2. 2 to the third is 8. And so this is the kind of thinking that we want to have here for this. How can I rewrite each side of the equation so they have the same base? And that's just by recognizing they're both bases of 2. So we get to rewrite 8 as 2 to the third power, then raised to the x, and then 4 is 2 squared. Now, I'm going to be a little bit deliberate here and take my time to make sure we understand where everything is coming from. Right now, you have 2 to the third to the x, so when you have a power to a power, we would multiply. So we end up with 2 raised to the 3x is equal to 2 squared. And now, since these guys have the same base, we can equate their powers. So 3x equals 2, which when we solve for x is 2/3. And that's not, dare I say, that's all we have to do, but yeah, really it is. So you just need to know your powers. See Art in the chat saying, I'm assuming that means natural log of x and not some kind of shorthand that this old guy doesn't know. Yeah, we could use natural log, but for these problems right now, you're going to see that I don't need a calculator for anything. Now, there will be a time when natural log is highly encouraged to use to solve these, but right now, no. It ends up being more trouble than it's worth. Now, we can have a lot of fun with this stuff. I could say, Yeah, you know what? I'll just do that. If I say 25 raised to the x plus 2 equals 1/5 to the... yeah, I'll just say this. I'll say to the x minus 5 power. Let's see what happens. All right. So when I look at the bases for each side of the equation, I've got 25 and I've got 1/5. And you might say, how in the world can I reconcile this? Well, think about what 25 is. 25 is 5 squared, so let's rewrite it like that. So it's 5 to the second power, then raised to the x plus 2. Now, can I raise 5 to a power to get 1/5? The answer is yes. And we saw that way back over here, right? This little nugget. A to a negative power, remember the negative power doesn't give you a negative number, it gives you the reciprocal, right? And that's what we're going to look at here. How would I end up with 5 in the denominator? That's having 5 to the negative first power. So we do that, and we should be good to go from here. Again, we have a power to a power, so we're going to multiply these guys together. And we have this product that we need to take care of on both sides of the equation. Please make sure that you distribute correctly. So 2 times x is 2x, 2 times 2 is 4, so we have 5 to the 2x plus 4. And then on the right side we have 5 raised to the negative x plus 5. All right, and now, since you have the same base on both sides, we take their powers and we set them equal to each other. So 2x plus 4 equals negative x plus 5. And then what we have is just a regular, simple linear equation to solve. In other words, get your x's on one side, get your constants on the other side. Now, again, I'm going to move my x's wherever I can make it so that the lead coefficient is positive. So I'm going to add x to both sides. And then I'm going to move the 4 over to the right side. So subtract 4. And now I have 3x equals 1, which means x is equal to 1/3. So a nice, fairly simple problem as long as we can identify what the common base is. I heard a dog trotting in my house. I wonder if they're going to come say hello. Someone's going to jump over the gate. I'm just waiting for it. Not saying that I know my dogs, but I know my dogs. I know what they're going to do. All right. So let's make things even more interesting. Let's do this. Let's do 216 raised to the 5x minus 9 is equal to 36 to the 9 minus 2x power. All right? Okay, so again, make sure that you're writing correctly so that it's very clear what's a power and what's not. So we should recognize that we have x's in the power, so it makes it an exponential equation. But we need to figure out if there's a base that's common for 216 and 36. Now, my suggestion is to start with the smaller of the two numbers, 36. And is 36 a power of something that you know? And I'm hoping that off to the side you can say, oh, well, I know that 6 squared is 36. And then that's a good way of looking at it. And then if you look at 6 doesn't break down, and 6 is not another power. 6 is 2 times 3. So you're kind of stuck with it just being 6 squared is 36. If I want to figure out what is 6 to the third, I just multiply 36 times 6. And if you do that, you end up with 216. So you start with the small one, and you would keep multiplying times 6 until you got to the other one, and you could see, oh, what? It only takes one step. 6 to the third is 216. So now we rewrite each of these. 216 is 6 to the third, raised to the 5x minus 9, and 36 is 6 squared, raised to the 9 minus 2x. And then it becomes the same thing that we just did on the last problem. You have a power to a power, so we're going to multiply these guys. All right, so that's 6 raised to the, it's 15x minus 27. And on the other side, it's 6. This is a 2. Kind of got messed up when I circled it. This is 18 minus 4x. So again, make sure that you distribute correctly. Pay attention to your signs. And now, since these bases are the same, we rewrite this equation using the powers. So 15x minus 27 equals 18 minus 4x. A nice linear equation, the kind of linear equation we just want to, curl up next to under a warm blanket on this cold night and just tell it how much we appreciate it for just existing. Now, let's move our variables. So I'm going to add 4x to both sides so I can move and have all the variables to one side with a positive coefficient. That makes me happy. It makes you happy. And now we're going to add 27 to move the constant to the right side. All right, so this gives me 19x equals 18 plus 27 is 45. And now we finish by dividing both sides by 19, so we have 45 over 19. Now, we would try to simplify that. 19 is prime, and it doesn't go into 45 evenly. So that's it. Nothing more to do. The key part here, though, is recognizing that we can find a common base for both sides of the equation. And again, if we can do that, life should be simple for us. All right, let's try another one. See, I love doing equations like this. They're fun. I get to work with powers. That makes me happy. I'm going to do 16 raised to the 3x plus 5 is equal to 1 over 32 raised to the, let's go 2x plus 3. Let's see what happens. Now, let's see if there is a base that's common for both sides. Now, if you look at 16, again, you might say, oh, I know 16 is a square. All right. So if I do 4 squared, that gives me 16. If I go to the next power, 4 to the third is 64. Right? You got to make sure you're in the right mindset that we're talking about powers. So using a common base of 4 is not going to help us out. Not that what I wrote there is wrong. It's just not going to give us the 32. Well, what about 16? Oh, so that was 4 squared, right? But 4 is itself a square. It's 2 times 2. So if you build this, and maybe you're not too comfortable with this, so start off small. You say, okay, let's work with my powers of 2. I would like to think that you could start off by doing 2 to the third to get 8. One more power of 2 would give you 16. One more power of 2 would be 16 times 2, which is 32. And now we see the numbers that we want to work with. So 16 can be rewritten as 2 to the 4th, and this whole guy's raised to the 3x plus 5. Now 1 over 32. I see that 32 is 2 to the 5th. But because the 32 is in the denominator, it would have meant a negative power on the 2. So 2 to the negative 5th. And then, of course, raised to the 2x plus 3. And same as it ever was. Power to power, so we multiply. So this is 2 raised to the 12x plus 20. And on the right side, it's 2 raised to the negative 10x minus 15. Let's make sure I did the math right there. Looks good. And now you have the same base on both sides. So we set those powers equal to each other. 12x plus 20 equals negative 10x minus 15. Nice linear equation. Solve it like we've always done. So it means we're going to move the variables first. And here I'm going to add 10x to both sides, so I have a positive coefficient. Always know what you're doing and why you're doing it. I'm moving that 10x, and I'm adding 10x so those guys go away on the right side. By moving the 10x to the left, it allows me to get all of the variable pieces on the same side. And the reason I'm moving over to the left is so that I can have a positive coefficient. Now, I could have moved the 12x to the right. I could have done that. It would have given me a negative coefficient. I still could have done it, but I know me and I know my pitfalls. I know my weaknesses, so I'm going to try to avoid negatives through legitimate means as much as possible. Now, if the variables go to the left, the constant here must go to the right, so I have to subtract 20 on both sides. That guy is gone. I now have 22x is equal to negative 35. Yes, I know I have a negative. Couldn't really avoid that here. But it's okay, because what I'm dividing by is a positive number. So more likely to be successful that way. So I end up with negative 35 over 22. Again, do your best to simplify. 22 is made up of 2 times 11, and neither of those is a factor of 35, so you're just going to be done here. So again, find that common base, and life should be nice and easy. Now, before we get into this next problem, let me just remind you of a couple things. So something that we've already talked about, we've already mentioned, is that when you have something to a negative power, that would give us 1 over a to that power. The other thing to watch out for is when you have a to a power that's a fraction. Now, we've talked about this probably a couple of weeks ago. A to the 1 over n means the nth root of a. The denominator of your power tells you the index for your radical. And we even complicated this just a little bit. So what if it's a to the m over n and not just 1? This still means that you have the nth root, and you could say it's the nth root of a to the m, or what is usually a better way to write this is that we would say the nth root of a, and then we would raise that whole expression to the n power. By doing it that way, it allows us to take that base and apply the root, which typically makes it smaller before you raise to a power and make it bigger. Just an easier way to approach that. So just keep all of that stuff in mind when we're working with these exponential equations. All right, so if I were to do, let's do this 125, I'll be nice to you here, at least for today, to the 2x minus 1 is equal to the 7th root of 25. Now, don't get so caught up with the power. Don't get caught up with the radical. We want to focus on the bases. 125 and 25. Is there a base these guys have in common? Now, as I mentioned earlier, start with the smaller guy. What is 25 made up of? Well, he's made up of 2 factors of 5, so I know that 5 squared is 25. Well, what if I go to the next power of 5? 5 to the 3rd. If I do 25 times 5, we end up with 125. So that's the key to unlocking this problem. So 125 gets rewritten as 5 to the 3rd power. And then, of course, we carry down that power, 2x minus 1. Now, this is where things get a little bit tricky. If you just kind of ignore the 7th root for a moment and focus on the 25, 25 is 5 to the 2nd power. That root that we have, that 7th root, means that we have a power of 1/7. As I was talking about here at the top of this page, the denominator of your power gives you the index for the radical. So If the index of my radical is 7, that means that the denominator of my power is 7. All right. Power to a power on both sides of the equation. So this is 5 raised to the 6x minus 3. Please make sure that you distribute correctly. This is not pre-recorded. Whoa! Maybe it is recorded. I just knew you were going to say that. On the other side, you have 2 times 1/7. And that is just going to be 2 over 7. Nope. I am getting ahead of myself. Sorry. That's 5 to the 2/7 power. I was skipping ahead. All right. So we can clearly see these guys both have the same base. So we can equate those powers. So 6x minus 3 equals 2 over 7. And now that we have just this equation, we should be okay. Now, a lot of people are going to look at that fraction and go, fractions, ew, I hate you. So like, why even here? Well, fractions are just numbers too. Now, if you don't like the fractions here and you feel like they're going to get in the way of you solving this, we have a workaround for that, and that's clearing fractions. The only denominator that we see here is 7. So if I take both sides of the equation and multiply it times 7, then we're going to get rid of that pesky denominator on the right side because the 7 and the 7 there, those guys reduce. So distribute on the left, we have 42x minus 21. On the right side, we just have 2. A nice linear equation, right? And the nice thing about this one, you don't even have to move x's because you only have one instance of the variable. He's already there on the left side. So 42x equals 23. And divide both sides by 42. So x equals 23 over 42. And again, as I mentioned before, double check to see if there's any simplifying you can do. Hopefully you can recognize that 23 is a prime number. It doesn't go into 42 evenly. And so that's all we have to do for the problem. That's it. Don't try to turn it into a decimal because the decimal is not going to be, it's not going to be nice if you do that. So this is totally fine. But yeah, that's solving exponential equations. And you can make them look bigger and nastier. And yeah, I'm starting linear algebra soon. May the odds be ever in your favor. Yeah, it's been a few decades since I took linear algebra. I wonder if it'd still be bad if I went back and looked at it now. I don't know. Really don't know. Now, I do want to talk about there are a lot of applications for the exponential. One of those is when we do compound interest. Now, I'm going to try to do some fun stuff here. We'll see how well it works out. So, for my math journey, well, sure, I love talking about myself. Now, I feel like for the most part, growing up, I always really liked math. My mom was a teacher, so I'd always get my hands on, like, the year ahead, their math workbook. I'd always try to buy math workbooks when we'd go to Walmart, just for fun, just for practice. I just really enjoyed it. It made sense to me. Probably, if I were aware enough, could have seen, boy, it might be, landing somewhere in that autism spectrum disorder thing, but being labeled or having an autism diagnosis meant something totally different back when I was a kid. I remember there were a couple of times in math that I didn't know what was going on. And I remember being really frustrated by that. Even solving, and I still remember doing this, having an equation like this, 2x plus 7 is equal to, let's say, 51. I should have paid attention to, the teacher, but I was so used to things coming so naturally that I just probably ignored that and said, I'm going to brute force my way to this. I'm going to figure this out. Not realizing that I don't have to guess and check to get the answer. And I've run into students that I've tutored that have done that. They just try to guess to get the answer. Like, well, you don't really have to do that, because if you use properties of algebra and you subtract the same amount on both sides, you start to peel away those layers until only x remains. So I would have a problem like this, and I still remember it clear as day, sitting in my parents' living room, up against the, close to the window, because I still remember the curtains there, and it would take me 10 to 15 minutes to solve a problem like this, because I was doing guessing and checking. And I don't know, I just missed out on something. And then the next time that I was really struggling understanding what should have been something kind of basic was in geometry, when we started doing those 2-column proofs, where you would have a statement and you would give a reason. And I didn't really understand why we were doing that, how it worked, and how it was supposed to work out. I just didn't get that. I could look at it and say, yeah, I believe that with the given information that the conclusion is true, but it was, how do I get there step by step? And again, it was one of those things that took me a long time to understand the importance of that. And that is, everything that you say in math has a reason for it. If I am subtracting 7 on both sides, the reason I can do that is because of the addition/subtraction property of equality. If I divide both sides by 2, that's because of the multiplication/division property of equality. The whole thing that we as kids and you as kids have said forever, whatever you do to one side of the equation, you have to do to the other side, because there's a property for that. And when I get down to x equals 22, we have to understand, what does that mean? What it means is that at the very beginning of this problem, we made certain assumptions. And one of those assumptions is that 2x plus 7 equals 51 is true. We assume that's true, and as long as that assumption holds, we can apply those properties, and we find out, okay, if this is true, then this next guy is true, and finally we get to the very end here where we say x equals 22, which means if I were to replace the original variable with 22, that's going to make it a true statement. So we're trying to figure out what's going to make it true. Now, there are times that we start off assuming that it's a true statement, but through legitimate steps that we make, we may end up with a contradiction. And now that I'm thinking about this, sometimes that's the way that we prove certain things in math. We prove it by assuming that the statement that we're trying to prove is wrong. For example, proving that the square root of 2 is an irrational number. And one of the ways of doing that is that you say, you know what? Let's assume that the square root of 2 is rational, meaning you assume that it can... Now, I'm not going to do the whole proof because I've not really practiced this. But you assume... Boy, thanks for giving me... This is really going to... So you assume that the square root of 2 can be written as a over b, where a and b are integers, and these guys don't have any factors in common. So you assume that. And with that assumption, you keep working through that assumption until you end up with the... why did I just lose the word? Until you end up with a contradiction. And so if you're false, if this assumption that the square root of 2 is rational ends up being false by contradiction, then that means that the square root of 2 was irrational to begin with. But yeah, I think a lot of people didn't do well with proofs. And I remember at one point in my geometry class, I was like one of 2 students out of like 30 that was able to do some of these more complicated proofs. But I had a fantastic math instructor for three consecutive years when I was in high school for Algebra 2, Pre-Cal/Trig, and the calculus. And he was so good. And I didn't realize this until I got to college. He had taught me so well that I was able to start college in Calculus 2 And then there's only like 1 day or 2 days that whole semester that I actually learned something I didn't know because I had such a great teacher in high school. And you might say, oh, well, there are a lot of great teachers in high school. Well, when your high school has 5 students in your calculus class and that's it, and you come from a very, very small town, I ended up being very, very fortunate that I had really good math and science teachers. So, yeah. Vector proofs. Those don't ring a bell. But anyway, I do a little bit about me and I've been teaching math for 26 years. And when I started college, I just chose a major in math because I like math. Wasn't sure what I was going to do with that. And I found out, I think I might have some skills for teaching math. So let me pursue that. Ever explored the philosophy of mathematics? No, not really. I don't know that my knowledge is all that remarkable. If you had taught this stuff 100 times, I would expect you guys to know things pretty well. There's still a lot that I need to learn. I got some books and audio to listen to. It's amazing. Sometimes those math books are actually pretty interesting. Although I will say sometimes they start to lose me, especially when they're doing statistic stuff. Which is why I have some stat books I need to go through. Compound interest. So, oh, cool. That works out. There you go, Christian. All right, so we're going to keep things simple with compound interest. Now, I'm not talking about simple interest because that's like really, really simple. But compound interest is this form. I almost wrote the wrong form. A equals P times 1 plus R over N to the NT. Now, the way that this works out, I want to make sure you understand this. The way interest is supposed to work is that you take some money and you put it in an account that earns interest. And when the account earns interest, it just gets put back into the account so that the next time it earns interest, it's on a new, larger number, which means you earn even more interest. Now, in this day and age in the economy, it's kind of hard to find savings accounts or interest-bearing accounts where you earn interest of any real substance. I know that like most of your traditional banks, your savings account for every $1,000 that you have in savings, every $1,000, you'll earn about 1 penny a month. It's for every $1,000. That's not a lot. That's a very, very low yield. But here's the way this works. Now, with interest formulas, there is the good if you're investing, there's the bad if it's interest that is being accrued on a loan that you're trying to pay back. So for this compound interest, the P is the principal, it's what you start with. This guy right here means that you're going to come back with 100% of what you invested, plus, a bit more of interest, a bit more of that. That's what the R over N is. So the R is your interest rate. Your N is the number of times per year that interest is compounded. So you might see things that say, earning interest at, 4%. It's compounded monthly. You're not getting 4% each month. You're getting 4% divided by 12 each month. So you're growing by 1/3% a month, which still really isn't all that bad. Now, what that means... So here's what that would look like if you did 4% compounded monthly for a year. So you have the 100% plus 4%, so 0.04 divided by monthly, so it's going to be 12. And if you raise this to the 12th power, because for 12 months, what would that be for the whole year, right? That means each month you're taking whatever you have and you're multiplying it times 1.04 divided by 12. For a whole year, you would have this rate of return. So again, the 1 is the 100%, but this leftover part, this 0.0407, that means that a 4% rate with monthly compounding for the whole year means you would grow by 4.074%. So it's actually a little bit more. The more times that you compound in a year, the smaller the amount of interest growth is, but the more total interest you'll have at the end. So if I do the same thing here, and I do 1 plus 0.04, and we divide this by 365. So suppose you're earning this spread over 365 days. But then you raise it to the 365th power because you have 365 days. Your rate of growth goes to 4.08, almost 4.081%. So it's a little bit higher. So that's kind of cool, right? I think it's neat. Now, if we are doing true investing, you typically do not just throw money into an account and then walk away. What you'd be doing is that you would maybe start off with a certain amount of money, but then you keep adding money to that each month. That way, your account is growing by your own injection of funds, but also by the interest that's being earned. And so that's how you can really talk about growing your wealth. Now, this is what you should be doing anyway. It doesn't even matter how much it is. If it's just $5 a week or $100 a month or whatever it is, you got to start somewhere and start putting that money away. And hopefully you can find an account. It's probably not going to be with one of your big banks, but look around for reputable places that are FDIC insured. And then keep putting money in there every month. So the idea behind that is that if you have some big expense that comes up, you're able to take care of that. So if you need to buy, new tires or new brakes, or you got to pay tuition, or, you get sick, whatever it is, that you have the funds to take care of that. Now, you could also be saving for something else, but you always want to make sure that you have that emergency fund set up first, because you don't want something like, oh, I need to get some work done on my car. You don't want that to be the thing that just ruins you financially, right? Prepare for that. Now, this is compound interest. And then there's continuous compounding. Now, continuous compounding is going to be where you don't have compounding that's happening at these discrete moments, like at the end of every month or the end of every week. But it's happening on this continual basis. Just like your life, yes, you celebrate a birthday, great, whoop-de-doo. But that doesn't mean that, you just now are 22 or whatever your age is. Your age is constantly increasing because you live on a continuous spectrum. So continuous compounding, to tackle that, we use Euler's constant E. And this is raised to the RT. Now, I know this looks kind of weird, like, why are we getting into new stuff? Well, it's super important. So E is an irrational number. Just like the square root of 2 is irrational, and pi, super irrational, super useful. But E is about 2.71828, and just keeps on going. Right? There's no pattern to that. It doesn't repeat. It doesn't end. Now, here's one way of defining E. Suppose that if you invest $1 at 100% interest, okay, you invest $1 at 100% interest, then you would have something that looks like this, that your final amount is going to be $1 times 1 plus 100% interest, that means just the number 1, right? Because 100% as a decimal is 1, divided by n raised to the n times t. So let's do this as n. So we're going to do this for, you do this for 1 year. Now, as I was showing back on the graphing calculator, the more times that you calculate your interest, the larger your value is going to be. Now, what happens here is that as n tends toward infinity, a tends toward e. Your final amount gets closer and closer to e. So, yeah, let me do this. If we take 1 plus 1 divided by 2, so suppose that you only have 2 compoundings. So you get 2.25. So you invested $1, you get 2.25. All right. What if I do this quarterly? So 1 divided by 4 to the 4th power. Now what you're going to see here is that this number is getting smaller. So we're going to go from 1.5 to 1.25. But the power is going up, which means we end up with a larger number. Suppose we do this every month. 1 plus 1/12 raised to the 12th. An even bigger number. Is there no end to this? There is an end. The larger the number, or the more times we do the compounding, the smaller that value is going to be on the inside. But then we're raising to a really large power. But again, we are just getting closer and closer. Let's do 2,500. We're going to be getting closer and closer to the value of e. So as these guys get larger, we're going to approach this value of e, 2.718. So even when we did the 2,500 times, so that's more than daily, not quite hourly, it's getting bigger and bigger. So that's where e comes from. Really cool number. Ties a lot of things together for us. All right, what's going on here? What in the world? What is going on? All right, so with these forms for both compound interest and the continuous compounding, these variables all mean the same. P is your principal, how much you invest. R is your rate as a decimal. T is time in years. The one thing that is different between them is that for compound interest, you have to specify how many compoundings per year you have. For continuous compounding, it's happening on a continual basis. Now, what ends up happening is that we will take this continuous compounding formula and we use it just like in a more general form. So we're really, I guess, continuous compounding comes from this form that says y equals y naught e to the k times t. Some people will look at this and go, that's a completely different formula, but I'm going to contend that it's not. It's the same formula. What does the capital P stand for? It stands for your principal. It stands for what your initial investment is, your starting value. Down here, you see y naught, or y sub 0. When you have a subscript of 0, that means your initial condition, your initial value, which is what your principal is. Now, instead of using R for my rate, I'm using K. And typically, a lot of times in math, K is the stand-in for talking about rate. T is still got to measure time. And in continuous compounding, that A means your final value. Oh, that's what the Y means down here. It's your final amount. So the reason we start to transition to look at this as a more general form is because when we're talking about exponential growth and then exponential decay, We don't want it to always be tied up in this continuous compounding formula where it's really just for money. We want to be able to use this for all kinds of situations. And for these problems, it all comes down to, can you use the formula correctly? Can you type things into the calculator correctly? So if we say something like this, if I say that we're going to invest $28,400 at, let's just make up something, let's say 5.2% interest, and let's say that we're going to compound it, let's do monthly, and then we'll check out what it would be if we do it continuously. So, for both of these, concept is pretty much the same. You've got to get the right formula, though. So if I'm doing monthly, I'm going to start with the formula. A equals P times 1 plus R over N to the NT. Oh, you know what I forgot? I forgot the length. Compounded monthly continuously, and let's say we're going to do this for, let's say we do this for 5 years. I was missing something. Now, if you want to get a good idea about what a final answer should be, we can kind of base it off of the simple interest formula. And this is going to be some heavy rounding that we do here, but just to give us a good number sense. Like, will my final answer make sense to me? Now, if I do something at 5.2%, and we're going to do this for 5 years, at the bare minimum, we'd be expecting a growth of 5.2% times 5, which would be 26%. So to make the math easy, let's think about that 26% more like 25%, which is a quarter. So I'm expecting my initial investment to grow by a quarter in the span of 5 years. All right, so if I'm just kind of doing some quick math over here, I expect to increase by a quarter of, let's just say this is like $28,000 instead of $28,400. A fourth of $28,000 is $7,000. So I'm expecting a growth of $7,000, which means at the end, $28,000 plus $7,000, I should have a final amount somewhere of like $35,000. Now that's on the low end. This is not taking into account the interest on the interest. And it's also, I've done some rounding down from 26% and rounding down from the 28,400. But again, I'm not going for accuracy, I'm going for number sense. So when I type things into a calculator, am I getting an answer that makes sense to me? So I'm expecting something that's close to 35,000. So let's see. My initial investment, so 28,400 times 1 plus. Now, if this were just 5%, you would say 0.05. So since it's 5.2%, just put the 2 at the end. We're going to do this monthly, so my denominator here is 12. And then my power is going to be 12 times t, which is 5. All right. So we just need to go to the calculator and see what it tells me. Let's clear this out. So 28,400, 1 plus 0.052 divided by 12, raised to the, now this is where I want to make a little point. For these newer TI-84 models, the TI-84 pluses, when you do the power, it gives you a superscript so you know you're in the power, and you could easily type 12 times 5. We get an answer that's, I'm going to write this down here. This is $36,812.13. Now, does that make sense with what we postulated? 28,000 plus 7,000 was 35,000. Yeah, that is, I mean, it's not exact, but it's definitely in the ballpark, right? Where if there were some error, maybe I didn't type in the 5.2 correctly, but it definitely makes sense. Now, let me go back here. I want you to be careful. I'm going to change the mode here. So instead of math print, it's classic. This classic mode is also what you would see if you were using a TI, like one of those other scientific calculators that has a two-line display. Oh, whoops. So that's 28,400. 1 plus 0.052. Now, so far, this is all looking the same as it was before. But now when I press the power button, I get that little... why have I forgotten the word on that? Yeah, it's called a circumflex, but... Anyway, yeah, so you get the power. Now, if I just do 12 times 5, because that's what I did before, let's see what we get. We get 149,000. See, that doesn't sound right. And the reason for that is because this expression that we have here, the calculator is taking this 1 plus 0.052 divided by 12, it raises it to the 12th power, full stop. And then it takes the result of all of that times 5, so that this product of 5 is happening in the wrong spot. It's not happening in the power like it's supposed to. It's happening down in the, where it's going to be multiplying the amount that you invested. So if you have a calculator that does your display like this, make sure that you use parentheses correctly. So when you get to the power, open your parentheses, and don't close the parentheses until you're done being in the power. So it's 12 times 5. And now when we hit enter, we get an answer that makes sense. And that matches up with what we're supposed to have. Now, on the other side here, we have continuous compounding. So for continuous compounding, your amount is P times E raised to the RT. So starting with the same principal amount, 28,400, E, and again, E is a constant, it's that special irrational number, RT. So my rate, 0.052 times the time, which is 5 years. Now again, you got to make sure that you type things into the calculator correctly. So, coming back over here, we have 28,400. Now you got two ways that you can do E. You can do second and then the division symbol, but then you have to do a little bit more work. Instead, do second and this button here that says LN. That's an L, not a capital I. So it's E, so it gives you the E, it gives you the power, and it gives you the parentheses. So 0.052. Now remember what I just said. When you open up parentheses for the power, don't close it until you're done. So I'm not done being in the power. I've got to multiply this times 5. Now I get an answer that's very close to what we had the first time. So it's $36,000 or $36,832.81. So as I was mentioning before, the more times that you compound, the more money you're going to have. Now we went from compounding once a month to compounding continuously. The change that we had over the span of 5 years was $20. Not a whole lot, right? But again, it is more. Now, when you see some problems like this that might show up in the homework, it's also going to ask you for, how much interest was earned. Right, so you've got your final amount, and then you would subtract off however much you invested. Now, so here, let me see if I can do this. I really want to show this to you because it's one of these like math in the real world things, and it definitely deals with what we've got going on here. Let me do this. Oh, hold on. I want to change to this. All right, let's do some Excel stuff. All right, so let me come over here, and let's just say that this is month, value, oops, an increase. Well, we've got to make this larger so I can actually see this. Who uses Calibri? Gross. Let's do... I really got to spend my time trying to find a good font. A little bit better. All right. So let's do month 0. Oh, stop it. Oh my gosh. Grab the right thing. There we go. Nope. Nope. There we go. My goodness gracious. Why that's so difficult. All right. So we're going to see what happens at the very end here. Let's do this for the 28,400. And then what we're going to see here is we're going to have this equal to the previous cell times 1 plus 0.052 divided by 12. Nope. Hold on. No, yeah, that's right. And this is going to equal this minus that. We got to do some formatting here. Format for money. Cool beans. And we're just going to bring this all the way down. All right. So what I hope that you can see here is that each month, the amount of money you're earning from interest is growing. Now, it's not growing a whole lot. Like the first month, you earn $123, and the last month, you've earned $129 from the previous month. But that's, it is growing. So you see that you're earning interest on interest. Now, I'm going to take the same stuff. I'm going to do that over here. And I'm going to change this up a little bit. So suppose that you can add, let's say $200 a month. How is that going to, how's it going to affect things? Yeah, so let me do this. Actually, that's will already be taken care of. So if you can inject your own money into your account, an extra $200, then you'll be able to earn even more money. So I'm going to, well, all right. So this is how much you would have earned in interest if you didn't do anything. And here, I'm going to have this equal to all of this minus the $2,400 that we put in ourselves. So by us putting in an extra $200, not only are we, of course, there's that natural building up of wealth, but we have also increased how much interest we would have earned in the year by $58. So again, not only do you have more money in the account, but you have also earned more interest over that year. Now, the same thing is going to be true if you're to be talking about like paying off bills. If you just pay the minimum amount each month, then it's going to take a while for you to pay it off. So if it says, oh, you've got a 5-year car note, or you've got a 30-year mortgage, it's going to take you that much time to pay off everything. But if you can pay extra, then that means that when interest is being accrued on the account, if you're paying extra, there's less of it there to grow. So that means you are working to you're working to fight the interest that way whenever you're paying more than the minimum payment. Because your minimum payment has to be large enough to cover the interest that has grown or that's been attributed to your account over that month, plus some extra to cut down the principal. But we could spend a lot of time looking at that, and we could have a really great discussion about, so what about those 50-year mortgages? So, hey, math man, what do you think? 50-year mortgages, is that a good idea or is that a bad idea? I'm going to tell you all right now that a 50-year mortgage is a very, very bad idea. So I did this example in one of my classes this past semester. And for, I think, what was the example? Like a home that would cost, say, is it $300,000 or $350,000? Not really sure that matters. The amount that you would be saving per month by going from a 30-year to 50-year mortgage, you'd be saving about $100. However, yes, it'd be $100 less per month. But that's $100 less it's like the difference between paying $3,500 a month versus $3,400 a month. So if your expenditures for a home, for mortgage and all the taxes and stuff that go with that is going to be $3,500, saving $100 is not going to be that big of a deal. You're not getting a big break on anything. Because the longer the term it is to pay off your loan, you typically have higher interest rate. So, let me show you what I'm talking about. Let's go back to the calculator. I can actually select the calculator. Where are you? Here we go. So, if you have a TI-84 like this, if you go to the apps, the first option here is finance. This thing that says TVM solver. Now, this is where the fun comes in. The N is going to represent how many payments you're going to be making. So if we're talking about, let's do this. Let's do a 15-year mortgage. So a 15-year mortgage for 12 months. And let's say the interest rate, because you're doing 15 years, they're going to cut you a break and they're going to charge you 5.5% interest. And you want to buy, let's say, a $300,000 home. Payment, we're going to find out what that is. The final value is, of course, going to be 0. Payments per year is 12. But this right here, this is how many times per year is interest accrued. Now, I used to be under the impression that it was, they're only doing interest at the end of the month, when you make the payment. Nope. Your interest on your unpaid balance, it's earning interest against you every day. So do this, and then for the payment, do alpha, enter to solve. Now, I'm going to go over here to a new page and write this down. So we have a $300,000 home. So a 15-year mortgage, and we're saying at 5.5%, the payment here is going to be $2,453.19. Now we're going to come back to that. Don't worry. Now, if we come back up here and we say, let's do a traditional 30-year mortgage. So 30 years times 12 months, so 360 monthly payments. Now, because you're taking longer to pay it, you might have to do 6%. This is still going to be our final, our principal value, and our payment. Let's solve for this. Oh, that's a whole lot less, isn't it? We're saving money now. So 30 years at 6%, your monthly payment is $1,801.45. Now, let's take a look at 6.5, or let's take a look at a 50-year mortgage. So a 50-year mortgage is 50 times 12, so 600 payments. And because you're taking longer to pay, they're going to charge you more interest because the bank is the one who's taking the risk here. And now let's see what that payment's going to be. So this is going to be $1,695.01. So you see that the difference there from a 30-year to a 50-year mortgage is a difference of about $100. Well, let's keep doing some math on that to really see what's going on. Yes, Art, the Trump administration, others are trying to say, well, this is how we can get people into homes by offering a 50-year mortgage. And I've had students, a student who worked at a bank, saying that they saw someone get approved for a 50-year mortgage. But you know what? We're not done with the math here. There's still plenty of math to go around. Boy, boy. Now, so I wrote the numbers down. We have, for a 15-year mortgage, so that was 15 times 12 months times $2,453.19, you can't forget that, means that you would have paid $441,574.20 for a house that costs $300,000, meaning that the bank gets $141,574.20 off of you. Okay? Let's do the next one here. We've got 30-year mortgage. Whoops. The wrong spot. So a 30-year mortgage times 12 months in the year times $1,801.45. All right, so that's $648,522. So the bank's profit is $348,522. But now, if you look at this, going from a 15-year to a 30-year mortgage, yes, the interest rate is higher. Yes, the bank is going to be making a whole lot more money off of you over that span of time. But your monthly payment is $650 less. So that's a significant amount. Right now, when you start the repayment, though, it's going to be fixed at $1,801.45. It's not going to go up or down unless you've got some kind of adjustable rate mortgage or you've done something else or you refinance. So it's going to be it's going to be that. It's not going to be changing. Let's look at your 50-year mortgage. 50 years, 12 payments, and that's $1,695.01. So that's $1,017,006, meaning that the bank will earn $717,006 from you doing that. Now, how does that make you feel? Now, the thing to understand here is that, you can always change that. So we wrote down the numbers here so you can see what's going on. So anybody thinking about doing a 50-year mortgage, please reconsider. The savings of $105 isn't going to be that much. Now, here's some other things to consider, which I think a lot of people don't, especially if you've never done home ownership. Now, things are going to be different depending on where you live, but around here, you have property taxes. Now, these property taxes will go to pay for the schools, the municipal utility district, waterworks, infrastructure, police, fire, all the stuff that we want, right? And so property taxes end up being about 3% of the assessed value of your home. So 3% of a $300,000 home is $9,000 per year. So this is what you're going to have to be shelling out every year, even after your house is paid off. And this is assuming that your house does not increase in value, right? Plus, don't forget about homeowners insurance. So homeowners insurance, you're probably looking at another, I'm going to be conservative here, and I'm going to say $3,000 a year. So, in addition to the monthly payment that you have here, you're going to have something that is around $1,000 per month on top of your mortgage payment. So we think about that. That means that for a 30-year mortgage, your payment is going to be about $2,800 versus if you do a 50-year mortgage, your payment's going to be about $2,700. Are you really saving money at that point? That's such a small difference between those two when you start to get to those high numbers that it just doesn't make any sense. The only person that it makes sense for is going to be the bank, right? And a lot of people would say, why would you even do a mortgage? Why do people do this? Well, I tell you why. Because I bet you don't have $300,000 just sitting around. And if you do, you're probably going to be looking for a bigger house anyway, right? So when I bought the house I'm in right now, I did not have the money in cash or in assets that I could liquidate to buy the house outright. So what did I do? I took out a mortgage, right? And so I've been paying it off diligently for the past, oh my gosh, has it been that long? No. For the past 15 years? Wait a minute. Yeah, for the past 15 years. Now, if I make extra payments, or if I pay more than that minimum monthly payment, then that means interest has less of a hold on it, and I can pay it off sooner, and I can take money away from the bank. Instead of them getting $348,000 in interest, they'll get less because interest doesn't have a chance to take a hold on it. But then you look at that 50-year mortgage, $717,000 in interest. That means for a $300,000 home, you've spent $1 million on just on buying the home. That's a lot of money, right? So again, if you can pay things off a little earlier, or pay extra on it, it definitely will help you out. Even something as small as like $100 a month for any of these mortgages, you'll pay it off a bit sooner. Now, I'm not sure how much sooner, but yeah, definitely worth checking out. Now, before we buy anything, always run the numbers, okay? Always run the numbers and know what it's going to be. Even if it's something like buying a car. Oh, I can get this great deal, and the interest rate's only 12%. 12% is a horrible interest rate. Now, no, it's just horrible. It's horrible. So you've got a calculator, like I was showing you. You can put in the numbers and see what it's going to be for you to, what your monthly payment's going to be. Anywho, I hope you found that to be useful. I know it's always eye-opening to my students because even on like that 30-year mortgage, it takes you about 21 to 22 years until you've paid half of the principal. So it wouldn't be until about year 22 that you've taken that $300,000 that you borrowed and you've cut that down to $150,000. Because those payments that you're making at the very beginning are so huge that you're not really making that much of a dent. Yeah. Anywho, well, that's about it for tonight. I'm sure I'll be back tomorrow. Not sure exactly when. Maybe another nighttime stream, we'll see. And probably try to get into some logarithms, which are super fun and super dope. So check it out. Anyway, thanks for being here. Thanks for the chat. Hope you guys have a great evening, and be number wise. Please do. Until next time, take care.